The enormous detonation is an idea that has outlined how we could unravel the universe, illustrating the supporting flow of cosmology as per Einstein's theory, otherwise called coarse-perusing cosmology. The massive impact was the moment the universe began its advancement, showing the production of all matter, energy, and existence. This event occurred around 13.8 billion years ago and led to the monster universe we observe today. However, recent advancements in cosmology suggest that the huge impact probably wasn't the absolute beginning. Instead, there could have been a phase before the tremendous blast that was equally fundamental in shaping the universe. This pre-period is known as boundless extension, and its development is potentially one of the most fascinating aspects of modern cosmology. It proposes that before the hot, dense phase of the enormous detonation, the universe went through an extremely rapid expansion. During this period, the universe was expanding in size at a stunning rate. To put this expansion into perspective, if the universe started smaller than a subatomic particle, it would have expanded to be vastly larger than the entire observable universe within a tiny fraction of a second, around 1/4,000,000th of a second. This inflationary stage did not last long, yet it played a crucial role in shaping the universe. When the inflationary phase ended, the energy driving this expansion was released into space, heating it up and creating the particles of matter that make up everything we see today. In many ways, this phase was the precursor to what we consider the huge explosion. While the theory of expansion is widely accepted in cosmology today, several unanswered questions remain. For example, we still do not understand what triggered expansion, what caused it to stop, or how long it lasted. These remain open questions in cosmology, and answering them is crucial for a deeper understanding of the origins of the universe. Before expansion, the universe existed in a marvelously dense, tiny point of matter, often referred to as a singularity. From this singularity, expansion began and eventually led to the formation of atoms, particles, stars, and galaxies. The idea of the giant impact as the absolute beginning is compelling, but modern cosmology suggests a more complex picture. Some theories propose that the universe underwent a phase before the immense impact, during which expansion caused it to grow at a mind-boggling rate, increasing in size by a factor of 1,000,000,000,000 within a fraction of a second. This rapid expansion was fueled by a peculiar form of energy that existed in empty space. Once expansion ended, the energy that had driven this growth transformed into particles, heating the universe and leading to the hot, dense state we call the huge explosion. This inflationary stage was cold and empty, but it set the stage for the formation of matter and the universe we see today. One of the more theoretical concepts in modern cosmology is the idea of immortal expansion. This theory suggests that expansion did not stop simultaneously everywhere. Instead, it ended in patches, creating many pockets, each of which could be a universe on its own. According to never-ending expansion, there could be a limitless number of universes, each with its own set of physical laws and constants. This is where the concept of the multiverse becomes essential. The idea that our universe may be one of many, or even an infinite number of universes. If this idea is correct, it could explain why our universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes, and we happen to live in one where conditions are perfect for stars to form and for carbon, oxygen, and other essential elements necessary for life to exist. While theories like never-ending development and the multiverse remain speculative, the concept of expansion itself is well supported by observational evidence. The strongest support for expansion comes from the cosmic microwave background, CMB, radiation, the oldest light in the universe. The CMB was emitted around 380,000 years after the huge explosion, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This light provides clues about the earliest days of the universe, helping scientists understand what happened shortly after the huge explosion and supporting the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images revealed subtle variations in temperature in the early universe, which matched the predictions made by inflationary theory. This experimental evidence strengthens the idea that expansion is not just a theoretical hypothesis, but a critical part of understanding the origins of the universe. Understanding the huge explosion and what preceded it requires uniting two of the most fundamental theories in modern physics. 1. Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe. 2. Quantum theory, which governs the behavior of particles on the smallest scales. The gigantic scope of the universe, including the structure of galaxies, stars, and planets, is described by cosmology, while quantum theory explains the behavior of particles on the smallest scales. To answer fundamental questions in cosmology, such as what the universe is made of and where it came from, scientists must develop a theory that unifies these two frameworks. This would allow us to understand the Big Bang as well as the conditions that led to it. One of the most astonishing aspects of the universe is its size. The most distant objects we can observe are about 47 billion light-years away, meaning the observable universe spans approximately 94 billion light-years across. This might seem paradoxical, given that the universe is only 13.8 billion years old. How can the observable universe be larger than the distance light could have traveled in that time? The answer lies in the fact that the universe has been expanding over time. As it expands, the distance between objects increases, making distant objects appear farther away than the time it would take light to reach us. Most scientists believe that the universe extends far beyond the observable universe. In fact, it is possible that the entire universe is infinite in size. The observable universe is merely the portion we can see, limited by how long light has had to travel since the Big Bang. There may be vast regions of the universe that we will never be able to observe. While it is possible that the universe is infinite, the question remains: is there anything beyond the universe? Most scientists are uncertain about this idea. If the universe is infinite, there is no outside of it. The universe would simply continue indefinitely. Even if the universe is finite, it may not make sense to talk about anything beyond it. Beyond would imply something existing outside of space, but space itself is a property of the universe. Therefore, the concept of beyond the universe may have no physical meaning. Just as the origin of the universe is a subject of intense study, so too is its ultimate fate. The current leading hypothesis is that the universe will continue expanding indefinitely. This is attributed to a mysterious phenomenon known as dark energy, which is driving the universe's accelerated expansion. Before the discovery of dark energy, scientists believed that the universe's expansion would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and begin contracting, leading to a big crunch. However, dark energy appears to be pushing the universe apart at an increasing rate. If this acceleration continues, the universe will keep expanding forever, eventually reaching a state where galaxies drift so far apart that they become isolated from one another. In this scenario, the universe would become cold, dark, and lifeless. Stars would burn out, galaxies would separate, and matter would eventually decay. This is known as the Big Freeze or the heat death of the universe. The story of the universe, from the Big Bang to its possible end, is one of the most profound and complex narratives in science. While we have learned a great deal about the origins of the universe through the theory of cosmic inflation and the study of the cosmic microwave background, many questions remain unanswered. What caused inflation to start and stop? What lies beyond the observable universe? Is there a multiverse, and if so, how many other universes exist? As scientists continue to study the universe using advanced technology and theories that bridge quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The journey to understand the universe is ongoing, and each discovery brings us one step closer to answering the fundamental questions about our existence. The study of the universe's origins and structure is not just a scientific pursuit. It also raises profound philosophical questions about existence, reality, and our place in the cosmos. One crucial area of interest in cosmology is dark matter, which is believed to make up about 27% of the universe's mass-energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is essential for explaining the formation and behavior of galaxies. Ongoing experiments and observations have provided clues about dark matter's properties, yet its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. However, no direct evidence of dark matter particles has been found so far. The search continues through a combination of laboratory experiments, astrophysical observations, and simulations that model how dark matter influences the large-scale structure of the universe. Another key area of investigation is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy accounts for approximately 68% of the universe's total mass energy content. Its discovery was unexpected and has led to numerous theories, including the cosmological constant and dynamic fields such as quintessence. Understanding dark energy is crucial, as it will determine the ultimate fate of the universe. Scientists are studying its effects on cosmic structures and trying to determine whether it remains constant over time or evolves. Beyond dark matter and dark energy, the study of large-scale structure formation offers valuable insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter clumps together under the influence of gravity, leading to the intricate structures we see today. Simulations run on supercomputers help scientists understand how these structures formed over billions of years and continue to evolve. Astrobiology also intersects with cosmology, as researchers seek to understand the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has accelerated in recent years, with thousands of exoplanets discovered. Some of these planets exist in their star's habitable zone, where conditions may be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet habitable. Finally, the role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that combines general relativity and quantum mechanics remains one of the biggest challenges in physics. Theories such as string theory and loop quantum gravity aim to bridge these two fields, offering explanations for phenomena like black holes in the early universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe by providing unprecedented details of distant galaxies and cosmic events. With each groundbreaking discovery, we move closer to unraveling the mysteries of the universe's formation, evolution, and ultimate fate. The study of the cosmos is a vast and intricate tapestry of scientific inquiry and philosophical reflection. From the fundamental forces that shape cosmic structures to the search for extraterrestrial life, our exploration of the universe is a testament to humanity's enduring curiosity. As we strive to answer these profound questions, we gain a deeper appreciation for the vastness and complexity of the universe.